Good morning, students. We start chapter 1, relation and functions. First, we see the concept of class 11th, Cartesian product of two sets. Let A is 1, 2 and 3, and we want to find A cross A. A cross A is denoting Cartesian product of two sets. Actually, I took here same sets, but it's very simple meaning. You remember that it is having element in ordered pair like 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2 and 3 3, having 9 elements. Next, I tell you relation, which is again the same as you studied in class 11th. Relation is none else. Relation is actually subset of Cartesian product, meaning what we found here, A cross A, your relation or defined relation on A will be none else, it will be subset of this A cross A. So I put one example for you. Suppose I am defining a relation R from A to A such that mod A minus B less than or equal to 1. So what is its meaning? Don't afraid. Your relation from set A to set A, and it's given by this one. You are having set A with element 1 2 3. So find out your all the elements which satisfy this one. So how it is? I tell you, A will be first element and B will be second element. So how many elements it will contain? You just have to go with this. In all cases, whatever you will take, this should satisfy. Let me take you one this element 1A and 1B, meaning this is A and this is B. 1 minus 1 0, which is less than 1, meaning it will contain in R. 1 2, 1 minus 2, which is minus 1, actually it is in mod, that's why it is 1 equal to 1, meaning 1 2 always also lie in this R. 1 3, 1 minus 3, it's actually minus 2, meaning 2, which is not less than 1 or equal to 1. It means 1 3 will not be in the set R. Now you student can understand that element 2 1, element 2 2, element 2 3 also will lie in that, because 2 minus 3 is minus 1. In mod it is 1, which is equal to 1. 3 1 will not lie in this set relation R, because 3 minus 1 is 2, meaning 3 2 and this 3 3 will lie in this relation. What you observed, that what I got a relation which is none else, it is a subset of A cross A. It is subset of A cross A. It is a subset of A cross A. This relation is subset of A cross A. Always it happens. I tell you one more example which we can simply say, and I would tell you some important thing here, which is one of the type of relation with this example. Suppose I am taking here relation R AB such that A minus B in mod is greater than 5. Very interesting that is. Let me explain something I remember right now. So I want to tell you here that This R is a roster form. The type of the expression of this R is a roster form, and this is a set builder form. So keep remember these two words, or you already have studied in class 11th. So I am taking here one more example of relation, which is this one, and with the same set. Suppose your relation is defined on A, and A is 1, 2, 3. So if you will go with how many elements it contains, very interesting that is, take one by one. Suppose this element you're taking 1 minus 1, which is 0, not equal to 5. 1 1 will not contain in that. 1 2, 1 minus 2 is equal to minus 1 in mod it is 1 is greater than 5. Wrong sentence it is, meaning 1 2 is also not containing that one. So in short, I would say that no element will satisfy this one, so that no element containing in that, meaning phi, null set. That is called empty relation. Please try to understand empty relation. A relation containing no element called empty relation. And one more example, which is actually very important to understand, that suppose I am defining like mod A minus B less than or equal to 2 is very interesting. So this, if you want to find out the element in that R, what you will get, guys? A minus B less than or equal to 2. If your relation is defining on A, meaning that A, and if you will find out elements like 1 1, 1 minus 1, 0 less than 2, 1 2, 1 minus 2 is in mod 1, it less than 2, 1 3, meaning minus 2 in mod it is 2 equal to 2, meaning all the elements will lie in that relation. What you observed? Your relation is actually equal to that A cross A. Your relation is actually equal to A cross A. In these two sets, to try to keep remember, when R equal to phi, it's called empty set, and when R equal to itself Cartesian product of two sets called a universal set, universal relation. It's a very important sentence. We finish here. Next, this was a recap. You already have studied in class 11. I only have revised all this, and further I will go on a new topic which is a major part of the day. We are going to study equivalence relation. What is equivalent relation? Before it, we have to go through 3 stages, and for that the short trick I'm telling you, which is R, S and T. So it's new, you will get it soon. First, reflexive, which is R, reflexive. Second, symmetry, this one. And third, which is symmetric, and third, transitive, T. Reflexive, symmetric and transitive. These are 3 more types of relation, and one by one I will explain all. Then finally I will reach on this particular word, equivalence relation. Before it, you have to go through all these 3 types of relation. So first I will explain what is reflexive, and don't forget this example. So I will tell you by these all examples, and I will explain what is reflexive. This is one of the type of relation. Okay, so let me speak something. What is a reflexive? First I'm telling you, let any relation R from A to A, then then relation R is reflexive if type of element AA belongs in R. Very important. For all A belongs to A. So this is a new thing, and you have to go through the definition of this. Again I read it. Let relation R defined from set A to A, then relation R is called reflexive when type of element AA, meaning both elements should be same, should contain in that R. So don't go far students. I explained you on this page that relation. So I want to take this relation again here. Suppose A is equal to 1, 2, 3. That was the same as I took here. And relation is again same, that relation defined from A to A, such that A minus B less than or equal to 1. Quick say me that. Tell me that what R is. This is 1, 1. This one. 1, 1, 1, 2. 2, 1, 2, 2, because all satisfy A minus B less than or equal to 1. So I'm repeating that same. 1, 1, 1, 2, 2, 1, 2, 2, 2, 3, 3, 2, and 3, 3. These all elements are the element of R because all satisfy A minus B less than or equal to 1. Now I'm telling you relation R is called reflexive when same element containing in R. Can you see this? 1, 1, 2, 2, and 3, 3. These three elements in that R. So R is called a reflexive. Please try to understand, students. See carefully that R having 7 elements, no matter at all, but 1, 1, 2, 2, and 3, 3. If these elements are lying in that R, R is called reflexive. Hope with example you got AA element should in R. Now I'm telling you second, which is symmetric. And what is symmetric? Let me explain. If AB type element in R, then R is called symmetric if BA also in that R. So this is again very interesting, and I won't go far. I would tell you with this particular relation which I explained here. What is the meaning of AB belongs to R and then so implies BA should in R? Can you see 1, 2 here? Can you see 1, 2? 1, 2, like AB belongs to R. 2, 1 also in R, like AB belongs to R, then BA also belongs to R. It means that R is what? Symmetric. Again, one more example. Look at 2, 3. 2, 3 A belongs to R. And if 3, 2 also belongs to R, it means the R is what? Symmetric. So, with the same example, I am telling you that R is, in that case, R is what? Symmetric. Third, transitive. Very interesting. If AB type element in R, ordered pair BC belongs to R, both should in R, implies if AC belongs to R, that R will be called transitive. Try to understand, very important thing this is. Both should in R, and if conclusion is AC also in R, R is transitive. If not getting properly, let me explain. See that R, I would tell you 1 2 uh, 1 2 and 2 3. Look at 1 2 belongs to R. Look at 1 2 belongs to R. 2 3 also belongs to R. And what says? AB belongs to R, BC belongs to R, AC also should belongs to R, then R will call transitive. 1 2 belongs to R, here it is. 2 3 belongs to R, here it is. But 1 3, can you see 1 3 here? No, 1 3 does not belongs to R, meaning R is not transitive. So I actually found the example of not transitive because it is very important example as far as all three concerned. So I only took this particular example to tell you R is not transitive. Again, let me speak. 1 2 belongs to R, 2 3 also belongs to R, but 1 3 not belonging in R, meaning R is not transitive. If it would be 1 3 also there in a set, I would say that, let me take one example also. Without taking in the set builder form, I'm telling you directly those two forms. Suppose it is having 1 2 2 3 1 3, only 3 element. So what do you think about that? I would say 1 2 and 2 3 are in belonging in that relation R. 1 3 also in R. I would say that R is what? Transitive. So these are this was a definition of all three, and this was very important. Let me tell you one more thing which I started with the equivalence relation, and I told you before it we have to go through all this, and I have one by one explained all. When AA type element in R, R is called reflexive, like 1 1, 2 2 and 3 3 belonging in R, R is called a reflexive. When AB is in R and implies if BA also in R, meaning R will called a symmetric. I have example here 1 2 and 2 1, like 2 3 and 3 2. These are in R. That's why this is R called a symmetric. And intransitive, when AB belongs to R, BC belongs to R, it should imply AC also belongs to R, then R will call it transitive. But I took the example of not transitive because it was very important example. You already have seen right now, that's why. Okay. In short, I would say when any relation from one set to another set is satisfying all these three, meaning R should be reflexive, it should be symmetric. If it is transitive, then R will call the equivalence relation. So in short, I would say that if R is reflexive, symmetric and transitive, then are called equivalence relation. So if you are told to prove that relation R is equivalence relation, you have to go through all, you have to prove one by one all three conditions, and then directly you can say that R is the equivalence relation. Okay, let me tell you one example. You can simply understand with this example. See, students, in your book, example number 2, page number 3. Let T be the set of all triangles in a plane, and R is a relation from set T to T given by T1 T2 such that T1 is congruent to T2. Show that R is equivalence relation. So the sentence is not new. The terminology now you got. You have to prove that R is equivalence relation, meaning you have to go through all three these conditions: reflexive, symmetric, and transitive. So one by one we'll prove all. How to prove all? Let me explain. Solution. First, I would say same element should be in R. Like, let T1 is any triangle of the set of all triangle. Let T1 be any triangle of the set of all the triangles. We know all triangles are congruent to itself. Very simple sentence. Very simple sentence. All triangles are congruent to itself. Any triangle is congruent to itself. So I would say that T1 is congruent to T1. In it meaning T1 and T1 belongs in R. Don't get confused. Your relation says T1 and T2 type element will be lying in R when T1 and T2 are congruent, meaning all triangles those are congruent in pair will be in R. When T1 and T1 are congruent, it will be in R. I repeat, T1 and T1 are congruent, that's why it will be in R. And when same element in R, relation R is what? Reflexive. Reflexive. Second, let T1 and T2, student, you have to remember how to begin the condition. If you want to find out or prove symmetric condition, you have to go with this term AB belongs to R. Then you have to show BA belongs to R. I wanted to show here that R is a symmetric, so I have to go first with this step that two triangle T1 T2 belongs in R. It means T1 congruent to T2. You have to go with this and you have to show T2 and T1 also in R. Like AB belongs to R, you have to prove BA belongs to R. So I started with T1, let T1 T2 belongs to R, meaning let T1 congruent to T2. You know that T1 and T2 are congruent, T2 and T1 will be also congruent. And it's not a special word, T1 T2 congruent, T2 T1 is also congruent. It means T2 T1 will be in R. Why? Because these two are congruent. I already have told you that if two triangles are congruent, that pair will be in R. When I started assumption T1 T2 belongs to R, T1 congruent to T2, when T1 congruent to T2, T2 automatically congruent to T1, and then T2 T1 belongs to R. So AB belongs to R, it means BA belongs to R, meaning R is symmetric. Now in third and last, how to start? How to begin? When AB belongs to R, BA belongs to R, that should imply AC belongs to R. So I have to go through first two assumptions. Let T1, T2 and T3, these three triangle in T such that T1, T2 belongs to R and T2, T3 belongs to R. And what to prove? T1, T3 belongs to R. So what is its meaning, students? T1 congruent to T2. And what is its meaning? T2 congruent to T3. And you know that when T1 congruent to T2, T2 congruent to T3, automatically meaning T1 also congruent to T3. When T1 congruent to T3, it meaning T1, T3 will be in R. Very simple. AB belongs to R, BC belongs to R. We have to take initially and we will prove that AC also belongs to R. Like T1, T2 belongs to R, T2, T3 belongs to R. We have to take initially these two and we proved that T1 also congruent to T3, meaning T1, T3 belongs to R. All since that R is transitive. And when all three proved, is equivalence relation. So students of the day, it is good enough. Now you do try example number 3 tomorrow, and find out also your doubts, and discuss with me at my personal WhatsApp number. Thank you.